So first let me say this video is dedicated to John Duffield, who bothered to ask me about some hastily written screed that I'd made a few years ago talking about this subject. And since photographs and phrases can only do so much, I thought that maybe a video would help. And so hopefully I found something that I'd done earlier, trying to keep track of stable isotopes. So if you look up the list of stable isotopes, for anyone who's not John Duffield, you'll probably want to have an image of this nearby to follow sort of what I'm discussing. But the basic idea is a model for the nucleus that focuses on tetrahedral neutrons. And in some sense, much like chemical models of electrons focus exclusively on protons and pretty much ignore isotopic differences most of the time, this model simplifies protons away a little bit. I guess that'll become clear as I talk a little bit more about it. But the basic idea is that this would be a neutron. This would be you've got a D4 here, and I've put sticky tack on two sides, and we'll call those sides negative. And imagine, if you will, that the protons that we would add to this neutron to turn into deuterium would be of negligible thickness, right? So this negative face, you take a triangle with two positive faces, if you want to sort of oversimplify things in this abstraction, and stick it to the surface of that face. And so that's what would let you transform from a neutron to a deuterium nucleus. Now, you could then add one more proton for helium-3, but then beyond that, you have no other faces, and I won't really talk about halo nuclei, but if you're interested, you should look that up. So, part of what we were talking about was tritium and helium-4 and what's going on with numbers of 5 nucleons. So this would be a model of helium-4, right? And so you can see here that we have one negative face remaining, but if you imagine that we need the ability for this to potentially flip or otherwise change or be hit by neutrinos or something, right? This configuration can do some kind of flip where this free negative face is now made to serve as the sort of mating face between the neutrons and protons involved, and you get back to the same state, right? So no matter how many times you flip this, you get back to where you were, right? Now, you're asking about tritium. So, if you have only one proton, and as John was describing, maybe it's sort of wedged in between. Well, if the proton is wedged in between the two faces, you'd get something that looks to the exterior like this. But if it's but there's two configurations for these. Basically, you can imagine that this free neutron is either attached to this neutron is attached to one of the positive or negative faces of this, and if it's attached to a positive face, then each of these two primary neutrons is only exhibiting one negative face at a time. But in a configuration like this, you have two negative faces on a single neutron, and as we know, neutrons in that state, something like a free space state, would decay eventually, right? And so, and then if your question is about adding a proton to helium-4, well, you no longer have that free negative face. Oops. And so, but if you have some kind of impinging energy that causes this sort of bond to break, then now you have a reason for things to fissure, right? So, so in some sense, helium-3 seems to be the exception to the rule. If you're thinking of open faces, or sorry, negative facets as a docking point for protons, but because otherwise you get a more brittle nuclear structure as opposed to something which may have the ability to maintain its form. There's more to be said. I'll show you real quick. I was talking about 5 neutron structures, so the ring would be here on the left and the star would be here on the right, but they both follow these same rules and keep one negative facet. Oops, I guess this one has an extra. But yeah, more to come, I guess.